Welcome. So this is a projectile motion problem, and the question says a ball is kicked from the edge of a cliff with a speed of 12 meters per second at 40 degrees elevation above the horizontal. So if we draw the cliff and then we draw the ball being kicked, this is 12 meters per second, and the ball's going to do something like that. And this here is 40 degrees. I'm sorry, I'm squeezing it in. I've got a lot of work to get into this space. And the cliff is 2 meters high, so it's 2 meters from here to here. And it says, what is the ball's horizontal displacement at the end of its journey? The end of its journey is when it hits the ground below the cliff, so this will be delta x. If you like, it's either the range, we can call it r, or we can call it the displacement in the horizontal direction. The displacement will actually be a vector, so it will have a beginning and an end, so that would be the displacement. So there's my brief visualization. And then I want to try to solve this problem, and as always, try and solve it in one step. So I'm going to say find delta x, my displacement horizontal, using, and the rule is if I want horizontal information, I will use horizontal information. So I'm going to use horizontal info. And now my job is to extract from this diagram all the pertinent horizontal information. And the first piece of information I have is that my initial velocity, way back here at the start of once the ball has left the foot, the horizontal information, horizontal initial velocity is going to be 12 cosine 40. We're using a component, and 12 cosine 40 is going to be 9.2 meters per second. It's positive because it's going to the right. And then the next thing we know horizontally is that the acceleration in the horizontal direction is 0 meters per second squared. There is no force acting in the horizontal direction. The reason why the ball keeps moving sideways horizontally is because of inertia, not because there's a force. If there's no force horizontally, there's no acceleration horizontally. And then the second thing we have is, and then the third thing we have is that I need to find my delta x. And that leaves two more things that I could know. I could know VF. And let's just talk about this for a minute. It turns out this is not a good way to go, but I want to show you it. So if I go using this, then an obvious expression is VF squared equals VI squared plus 2A delta x. So it seems like this is an easy problem to solve, until you realize that this A is 0 horizontally. And if A is 0, this whole term goes away. So we end up with VF squared equals VI squared, which is fine, it's true, but it's not what I'm trying to find. So that's no good. We need to be a bit careful here. Another question, another possibility comes up. Forget about V final. Let's think about delta t. And then the expression that comes up, I'm going to put a line here so I don't get confused. And then the expression is that delta x is equal to VI delta t plus 1/2 A delta t squared. And here, of course, yeah, a is still equal to 0, and so that term goes away. But all that means is we end up with a nice, relatively simple expression which says delta x is equal to vi, and we just said that vi was 9.2 times delta t. The problem is, I don't know what delta t is. So it's a two-step problem. So let's try and do the second step. So I'm going to say find delta t using, well, we clearly didn't know delta t using the horizontal axis, so let's try to find delta t using the vertical info. 9 times out of 10 you find delta t using the vertical information. So now I'm looking back at my diagram and I'm saying vi is equal to 12 sine 40, and 12 sine 40 equals 7.7 meters per second. Again, it's positive because it's the vector is pointing upwards. And then my acceleration now is equal to minus 10 meters per second squared. And I actually know the displacement in the y-axis. Remember, delta x means displacement. I'm dealing with displacement in the y-axis. And this is not just 2, but we start off at the top and we end at the bottom. So the displacement is downwards. That is an important point. So this is not 2, but it's minus 2 meters. And frankly, if we said this was plus 2 meters or just 2 meters, we'd be talking about a point somewhere up here. And the ball might reach that point. So we could get just an incorrect answer. But it is minus 2. And then we want to try and find delta t. And we can try and figure this out. So I could say, well, delta x is equal to vi delta t plus 1/2 a delta t squared. It's the same equation as I'm using up here, but it's a completely different context. Minus 2 is equal to, it's going to be 7.7 times delta t plus 1/2 times minus 10 times delta t squared. This is a quadratic, so let's write it in the standard form. We're going to say 5 delta t squared minus 7.7 delta t minus 2 equals 0. And this is an important step. So I need to just backtrack a little bit and make sure I did that rearrangement okay. 1/2 times minus 10 is minus 5, goes to the other side, becomes plus 5. 7.7 is positive, goes to the other side, becomes negative. Minus 2 stays where it is, so it stays as a negative. Okay, I need to solve this. So let me change the color of pen so things are a bit distinct here. Let me come down here, let's draw a line. Let's draw a line. And what we'll say is, oh yeah, delta t is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So delta t is equal to minus 7.7 plus or minus the square root of minus 7.7 squared minus 4 times 5 times c is minus 2. let's continue that guy across there, all over. 2a is 10. So delta t is equal to minus and minus x plus, so it's 7.7 plus or minus, and this is going to be 7.7 squared minus 4 5s are 20, 2 20s 40, but now minus and minus x plus. So it's 7.7 squared plus 40, which comes out to be 99.3. So this would be the square root of 99.3 over 10. And let's be a bit smart here. Let's do this. Let's just get rid of that negative sign. There's one of my answers. And then underneath it, let's just put the other answer. Delta t is equal to 7.7 minus the square root of 99.3 over 10. And it turns out that 7.7 plus square root of 99.3 over 10 equals 1.8 seconds. And actually, let's be a bit more precise than that. Let's be careful because I'm not at the end of my problem. Let's say 1.77 seconds. And then 7.7 minus the square root of 99.3 over 10 is going to be minus 0.23 seconds. Now, what do these correspond to? Two answers. Well, the clock is here when it's 0. So positive time runs forward, and when you're here, the clock is reading a positive value, and that's the 1.77 seconds. The negative is what the clock would read here if you imagined the projectile traveling up from the level of the field below the cliff. So this is not an unrealistic number. It's just not what we are interested in. Okay, almost there. So now what we do is we take our sensible time and we bring it up. And we say, well, delta x is equal to 9.2 multiplied by 1.77, and that will equal 16.3. And I look to the side, and there it is, 16.3. So there's a lot of things going on here. We visualized. We tried to solve it in one step. This was the blue bit. We found we needed time, and so we tried another axis to find time. We ran into a mathematical complexity in that we needed to find the roots of this quadratic. We carefully found the roots of the quadratic. We found there were two answers. One was clearly sensible. The other one was not unrealistic, but not what we wanted. We substituted the sensible one into our answer, into our equation, and there we had our answer. There we have it.